air-fuel mixture, a high level of compression, and an ignition system which has optimal timing and powerful sparks. Optimal ignition timing and powerful sparks are the responsibility of the ignition system. There are various types of ignition systems. In this video, we will mainly use a fully transistorized ignition system to explain the functioning of the ignition system. In this video, we will look at first, the structure of the ignition system. Second, how a high voltage is generated. Third, control of ignition timing. Fourth, spark plugs, which use the high voltage to emit sparks, igniting the air-fuel mixture. Fifth, other ignition systems. And finally, inspection and adjustment of the ignition system. In a gasoline engine, spark plugs ignite the compressed air-fuel mixture and generate combustion, providing power. So the ignition system must be able to produce a high voltage in order to provide optimal ignition timing according to the engine's operating conditions. First, let's take a look at the components of the ignition system and their function. Electrical power is provided by the 12-volt battery. The ignition switch. The ignition coil and igniter convert the battery's low voltage into a high voltage. This is relayed by the distributor to each cylinder's spark plug. This distributor incorporates an advancer device to obtain optimal ignition timing. A distributor with a built-in ignition coil is called an Integrated Ignition Assembly, IIA. The charge from the ignition coil creates a spark at the spark plug, igniting the air-fuel mixture. Spark plugs require a high voltage of more than 10,000 volts to generate sparks, but as we have seen, the vehicle's only source of electrical power is a 12-volt battery. So how do we generate a high voltage from a 12-volt power source? Let's explain. Take a look at this experiment. A 100-volt lamp is connected across the battery and the switch is turned on. The voltage is only 12 volts, so the lamp doesn't light. Next, a coil is connected across the lamp and the circuit switched on once more. Once again, the lamp fails to light. But at the instant the switch is turned off, the lamp flashes. Here's why. If the switch is turned off when current is still flowing in the coil, a large electromotive force, EMF, or voltage, is generated, flowing in the opposite direction. This is called the self-induction effect, and the electromotive force generated is called the counter-electromotive force. Next, let's do another experiment. Two coils with different thicknesses of wire and numbers of windings are connected in series. The moment the switch is turned off, the flow of current in the primary coil is cut, generating a greater current in the secondary coil. When the current is switched on and off in the primary coil, a high voltage is generated in the secondary coil. This is called the mutual induction effect. An ignition coil integrates these two coils into one. Let's conduct a test with an actual ignition coil. The current flowing in the primary coil is turned on and off. As you can see, the ignition coil uses the self-induction and mutual induction effects to generate a high electromotive force of tens of thousands of volts from the 12-volt power source. Conventional systems use conductive breaker points in the distributor to turn the switch on and off mechanically, just like this device. But today, most systems make use of the switching effect of a transistor or an electronic control unit, or ECU. Now let's take a close look at how a high voltage is generated using an actual transistorized ignition system. An ignition coil, a signal generator, and an igniter are integrated with the distributor. In the transistorized ignition system, the ignition signal from the signal generator is transmitted to the transistor in the igniter. This transistor turns the primary current in the ignition coil on and off. The signal generator has three components: a signal rotor, which makes one turn for 2 revolutions of the crankshaft, a pickup coil, and a permanent magnet. The rotor turns clockwise or counterclockwise depending on the engine. As the rotor turns, a voltage is generated in the pickup coil. This is the ignition signal. But why is a voltage generated? The magnetic flux of the permanent magnet flows through the signal rotor, the pickup coil, the bracket, and returns to the magnet. When the rotor is still, there is no change in the magnetic flux. When the signal rotor rotates and a rotor tooth approaches the pickup coil, the magnetic flux density increases. As the rotor tooth moves away from the pickup coil, it decreases. This means that the voltage generated in the pickup coil depends on the changes in the magnetic flux. The level of EMF generated depends on the relative positions of the rotor and pickup coil. When a rotor tooth approaches the pickup coil, the EMF increases, and when the rotor tooth and the pickup coil face each other, it becomes 0. When they move apart, a counter EMF is generated. These changes in the EMF cause the igniter to switch the primary current on and off. Let's take a look at how the current is turned on and off. When the engine is running and one of the signal rotor's teeth approaches the pickup coil, the voltage is generated in the direction shown in the diagram. The base current flows in the transistor switches to on, and the primary current flows in the coil. When the signal rotor's tooth is aligned with the pickup coil, the voltage generated in the pickup coil decreases and the transistor is turned off. This cuts off the primary current and generates a high voltage in the secondary coil. The transistor is also turned off when the voltage is generated in the opposite direction in the pickup coil. In this way, when the engine is running, the transistor is turned on and off every time one of the signal rotor's teeth passes the pickup coil. Every time the transistor is turned off, a high voltage is generated in the secondary coil. The voltage generated in the secondary coil then passes from the distributor's center electrode through the rotor and from the outer electrode to the spark plugs, according to the firing order of each cylinder. Next, let's take a look at the method used to obtain optimal ignition timing. In general, a gasoline engine achieves maximum efficiency if the combustion pressure in the cylinder reaches maximum when the crank angle is about 10 degrees past top dead center. This means that ignition should be timed accordingly. This graph shows the process in terms of the pressure changes inside the cylinder. Even if ignition takes place at point 1, combustion doesn't start immediately. Instead, combustion starts at point 2, and compression starts to increase. The compression reaches maximum at point 3, and combustion comes to an end at point 4. The period between 1 and 2 is called the ignition delay time. For a given fuel, this delay is more or less fixed, irrespective of the engine speed. So let's think about what happens if the engine speed increases. Because the ignition delay time between 1 and 2 is constant, the angle through which the crank rotates in the same period of time increases. The point at which maximum pressure is reached lags behind 10 degrees. So in this case, it is necessary to advance the ignition timing. If the load on the engine increases, the volume of the air-fuel mixture and the compression pressure inside the cylinder increase. The temperature of the air-fuel mixture goes up, and so the mixture burns faster. As a result, the combustion time gets shorter. This graph shows what happens. In this case, the ignition timing has to be retarded. It is changed according to the engine speed and driving conditions. This is achieved by altering the ignition advance angle, which is controlled by the advancer incorporated in the distributor. Ignition timing is controlled by a governor advancer according to the engine speed and by a vacuum advancer according to the load on the engine. The governor advancer controls the ignition advance angle by rotating the signal rotor slightly relative to the distributor shaft. And the vacuum advancer controls the advance angle by changing the position of the pickup coil. Let's take a closer look. The governor advancer consists of a cam plate, flyweights, and governor springs. The cam plate rotates together with the distributor shaft. Two flyweights rotate on the cam plate with support pins as their centers. At low engine speeds, the flyweights are kept closed by the force of the springs. As the engine speed increases, the flyweights are gradually thrown outward by centrifugal force. Then the cam plate moves the signal rotor in the direction of rotation until the centrifugal force balances the cam spring force. This operation controls the advance angle. This graph shows the relationship between the degree of the advance angle and the engine speed. Next, let's take a look at a vacuum advancer. Here, a diaphragm is connected to the pickup coil with an advancer rod. This diaphragm responds to the vacuum in the intake manifold. When the load on the engine is light, the throttle valve opening is also small, so a vacuum is generated at the diaphragm, pulling the advancer rod, moving the signal rotor to the left, and advancing ignition timing. When the engine load is heavy, the accelerator pedal is depressed, the throttle valve opens wide, and the vacuum in the intake manifold decreases. Then the spring pulls the diaphragm to the right. As a result, depending on the engine load, the pickup coil moves in the same direction as the signal rotor's rotation, retarding ignition timing. In automobiles, various types of vacuum advancers are used according to engine specifications. This graph shows the relationship between the intake manifold vacuum and the advance angle. The role of the spark plug is to reliably generate strong sparks and thus ignite the air-fuel mixture. The ignition sparks jump between the spark plug's center and earth electrodes. The spark voltage is high or low in proportion to the spark plug gap. Through normal use, the gap will increase, causing the engine to misfire during acceleration. Therefore, the spark plug should be inspected periodically to maintain optimal spark gap. Let's take a look at electronic spark advance, ESA. Instead of a mechanical advancer, an ECU or electronic control unit controls ignition timing in this system. This system senses engine conditions based on signals from various sensors. The ECU determines ignition timing and turns the primary current on and off. As this graph shows, conventional mechanical advancers could only control ignition timing in direct proportion to the engine speed and manifold vacuum. But using sensors and the ECU, ESA can achieve control closer to the ideal for the engine's running conditions. In ESA, the distributor has two integrated pickup coils, one of which generates an engine speed, or NE signal, and the other of which a crank angle reference position, or G signal. While the engine is running, these signals are continually transmitted to the ECU. In case of the D-type EFI engine, other sensors are provided for the ECU, such as the vacuum sensor, throttle position sensor, NOx sensor, water temperature sensor, and vehicle speed sensor. Next, let's take a look at a direct ignition system, or DIS. Conventional ESA generated a high voltage with one ignition coil and sent the voltage to each spark plug with the distributor. But a DIS transmits ignition signals to multiple ignition coils and distributes the power from the ignition coil directly to the spark plugs. Let's have a look at a standard ignition system. Unlike a transistorized ignition system, a standard ignition system turns the primary current of the ignition coil on and off mechanically, using the distributor's breaker points. The rotation of the cam on the distributor shaft opens and closes the breaker points. This turns the primary current of the ignition coil on and off. Now let's take a brief look at inspection and adjustment methods for the IIA ignition system. You can tell the engine condition from the color and condition of the spark plug's electrodes. A light brown color like this shows that the engine is in good shape. If the electrodes are black, like this, the air-fuel mixture may be too rich, or the spark plug heat range may be too high. If the electrodes are white, the air-fuel mixture may be too lean, or the electrode heat range may be too low, causing the electrodes to scorch. Please clean the electrodes with a spark plug cleaner or a wire brush. Next, check with the spark plug gap gauge whether the spark gap is within the correct range. If the gap is out, bend the outer electrode to adjust the gap. In the case of a platinum-tipped spark plug, the tip of the center electrode and the opposing earth electrode are thinly plated with platinum. In principle, in order to protect the electrodes, they should not be cleaned. But if it becomes necessary to use a spark plug cleaner, for example, because of soot, clean the electrodes as quickly as possible. It is not necessary to adjust the gap of a platinum spark plug. Inspection of the high-tension cords. Measure the resistance of the high-tension cords with an ohm meter. Inspection of the ignition coil. Measure the resistance of the primary and secondary coils and check that the resistance is correct. Next, measure the resistance of the pickup coil. To inspect the air gap with a non-magnetic feeler gauge, measure the gap between the signal rotor and the pickup coil projection. In the case of ESA, measure the gap between the NE signal pickup coil and the G signal pickup coil. Also measure signal generator resistance. To inspect the vacuum advancer, disconnect the vacuum hose and connect a vacuum pump to the diaphragm. Apply a vacuum and check that the vacuum advancer operates correctly. When inspecting the governor advancer, turn the rotor forward, release it, and check that the rotor quickly rotates backward. And check that the rotor doesn't rattle. Next, inspection of ignition timing. First, connect the tachometer and timing light. Disconnect the vacuum hose from the distributor subdiaphragm and plug the end of the hose. Then set the initial ignition timing. With the engine idling as specified, use the timing light to check that the ignition timing is correct. If the engine speed is high at this point, the governor advancer will operate, so be sure to check this with the engine idling. If the ignition timing is incorrect, loosen the distributor bolts and turn the distributor. ESA has a different inspection procedure. Let's check it out. First, connect the tachometer. Then use the SST to short terminals T or TE1 and E1 of the check connector in order to prevent the correction of the advance angle, and set the initial timing. With the engine idling as specified, check that the ignition timing is correct. Please refer to the repair manual for the reference value. This video has explained principles, construction, and operation of an ignition system. The ignition system is essential for the smooth operation of the engine. We hope that this video and the other reference material